Thank you for coming tonight. My name is Paul Dimotakis, and I'm the Chief Technologist at JPL. I'm also a Professor of Aeronautics and Applied Physics at Caltech. And it's my distinct pleasure to introduce to you my friend and colleague, Nate Lewis, who is going to talk to us about how we might power or repower our planet. Nate is the George Argyros Professor of Chemistry at Caltech, the author of over 200 papers, has graduated more than 50 PhD students. He started his academic career at Stanford. Nobody's perfect. And came to Caltech, has received a very large number of awards and distinctions. His own research has to do with solar energy conversion of various kinds, but I don't think he will be speaking to us about that tonight. He's also known for having developed the electronic nose, which is a device that can actually smell, has a number of sensors, and by combining the output of these sensors can actually distinguish different specific chemicals. It has flown on the shuttle, and it is qualified and will be taken to the space station to monitor substances that one would like to have early warning on. So thank you for coming tonight. I will get out of your way so that we can hear Nate. Thank you.
Thanks. Let's see if this is perfect. Thanks very much for coming. Paul didn't mention that the most important member of JPL out of all of the key employees is the project manager in charge of flying that electronic nose onto the space station. I eat dinner with her every night, so very proud of that. I'm going to tell you about a topic which is both humorous, and I hope you laugh at all the jokes, because without them it would be so serious I don't know we could actually get through it, and that's energy. I tell people in good conscience that energy is the single most important challenge facing humanity in the 21st century. Now I have to tell you why that is, and that will be in fact what we'll spend the whole hour talking about. I'll tell you about three things. I'll tell you about energy facts that set the scale of how big energy is. Those are undisputed. That's what we have now. You can look them up in any book on energy. And I have one color set of slides in the background so there can be no dispute about what is undisputable facts and what is the future, which is a different color slides. And you need to remember one thing out of this. I know audiences teaching general chemistry as I do can only remember three things. So the one thing I want you to remember here is the Stone Age. You have no idea why I've told you to remember that yet, but you will in about 15 minutes. Then I'll tell you what the future is likely to bring and why this is such a big problem. And to deal with that, you have to remember one number. That number is 3,000 years. And then I'll tell you, if you want to do something about this problem, what the challenges are to meet that scale and where the physics of our planet says that we can get that much energy. And to remember that, you need to know in about 45 minutes the answer to the question is Willie Sutton. Those of you who don't know who Willie Sutton is or do have no clue why I've told you that yet. But I guarantee you in 45 minutes you will. Many people ask me for copies of my slides. You can just download them off of my website and tell your friends. The video version of this is on the Caltech streaming video series in the Watson lectures. I see people watching it in Starbucks, much to my delight. I'm happy to have the word disseminated. I'm not the only one. Rick Smalley, inventor of carbon nanotubes and buckyballs and Nobel laureate, Spent the last 3 years of his life before we lost him to leukemia going around the country with myself and others as he testified in Congress that energy was the single most important challenge facing humanity today. Our trade journal, Chemist, Chemical Engineering News, said it was the most important scientific and technological challenge facing us in the 21st century, not just today. Pundits are saying it, like the new book that our columnist in the New York Times and my good friend now Tom Friedman is saying, that it's blindingly obvious what we should be doing. She's making the quest for energy independence the moonshot of our generation. Academics are saying it. Susan Hockfield is the president, 2 years old, of MIT, inaugurated 2 years ago. And she said the time for progress is now in her inaugural address. And she said it in a way that I think is very important. It is our responsibility, ours being both as scientists and engineers and as the general public, to lead in this mission. Because many reports, including those co-authored by myself and Rick Smalley and others, have shown that we are so underinvested and so beyond where we need to be that if we wait for the federal government to deal with this problem, it will simply be too little too late. We have to find a way to lead. Energy is so big that you need its own set of units to describe it. We're all familiar with watts. No one really knows how much a barrel of oil equivalent is or how much a cubic foot of natural gas's energy is, but we all know watts. A laptop now is about 10 watts, but used to be about 1, so we'll call it a watt. 1,000 laptops are a toaster. Don't leave your toaster on very long in your house because your average home electricity is about 1 kilowatt, which is about a hairdryer or a toaster. See a nice electric bill if you left it on for all night, that's for sure. 1,000 toasters is 1,000,000 watts. A megawatt is a small jet engine. 1,000 jet engines is a gigawatt. That's the output electricity on average of a typically sized nuclear power plant. I'll come back to nuclear energy later. And 1,000 nuclear power plants is 1,000,000,000,000 watts. That's the electricity demand of the world. I have to explain to many audiences, but I'm sure not this one, that this picture wasn't all taken at once. Nevertheless, you can still see the difference in electricity consumption between the haves and the 2 billion people that have not. You can see the difference clearly of where the 38th parallel is between South and North Korea, the haves and the have-nots. You can see places where there's poverty. You can see places where there's no education, because you can't be educated when you only have 1 candle and your school child can't study when it burns out every night. And you can't fix most of society's top 10 problems without enabling those people to have energy, because without it, you can't cure disease. Without energy, you can't stop fighting wars over oil. Without energy, you can't get out of poverty. Energy is the enabler for all of these other things. But even this 1 trillion watts of electricity demand on average, don't confuse that with our energy demand, because the electricity comes from somewhere. If you add up all the energy that we use, it's 14 trillion watts is the average rate of energy consumption. That's counting all the oil, gas, coal, nuclear energy, and all the heat content of all the energy combined that we use to power our planet in the year 2006. These are 2001, it was 13. We're pushing 14.5 right now. 85% of that comes from fossil energy. The rest comes from other sources. The United States consumes 96 quadrillion British thermal units in a year, if you read our National Energy Report. I don't think even the authors probably knew what that meant in terms of terawatts, but I guarantee you it's 3 trillion watts average consumption rate. The United States, with not 1/4 of the world's people, consumes 1/4 of the world's energy. But I won't talk anything more about that incredibly important factor as it relates to geopolitics of energy and our national security debate. The reason I won't talk about it anymore is because the Earth is round, and we're going to get that energy from anywhere we need it, because otherwise the lights go out. Sure, it's true that we fight wars over energy because humans have always fought wars over natural resources. Sure, it's true that some countries might have people that don't want to sell us their energy, and we know what we would do. We would just go to war, take over their country, and make them our friends and buy their energy. We know we're going to get it all. It's not a question of being denied energy as a society. It's a question of using it effectively. 85% of that 14 trillion watts comes from fossil energy, oil, coal, and gas, roughly equal parts oil, a little bit more now. Hydroelectricity is 2/10 out of the 13. Biomass is 10%. It's 1 terawatt. But this is unsustainably burnt. This is deforesting much more rapidly than you can replant and decropping. And the sustainable portion of that is in the total renewables column, which is 2/10 of a terawatt out of 13. And nuclear provides 0.9. Now, the astute amongst you will probably know that we only actually generate about 0.4 terawatts of electricity, but that's because nuclear power just makes heat, of which only about a third of that goes into electricity generation. That's secondary energy in the same way that this is the heat content of burning coal, only about a third of that of which goes into making electricity. This is the primary heat content on a fair footing of all the energy we use on our planet in a typical year. So don't talk to me about saving enough energy to take 2,000 cars off the road or saving enough energy to change the light bulbs in Fresno. That doesn't matter. What matters is trillions of watts. That's the scale of energy. Maybe it'll run out. I've added up for you all the proven reserves and the resource base of both conventional and unconventional oil, coal, and gas, and divided by an average recent year consumption rate. 1998 happens to be my base year. And you can see that dividing the proven reserves, which the SEC lets a company or a country book and tell its stockholders with 90% confidence that's in the ground, we have between 40 and 80 years worth of oil. We have between 60 and 160 years worth of gas, and we, both globally and in the United States and China, have over 200 years worth of coal. Some people look at this and say, we're going to run out of oil in 40 years. But it's been this ratio of 40 years for the last 100 years. Since the day after oil was discovered, we had 40 years worth of proven reserves of oil. The reason is that when it costs you $1 million a day to drill an oil well today in the Gulf of Mexico, and when only 1 out of 4 such drills are even striking oil and the other 3 are dry, you invest enough money to prove out 40 years worth of reserves. It doesn't pay to prove out 100 years worth of reserves and leave it in the bank. You return the rest to your stockholders or to your country. What matters more is how much the USGS estimates there is to be had, the resource base. With 50% confidence, they estimate that we have between 50 and 150 years worth of oil, between 200 and 600 years of natural gas, and almost 2,000 years of coal. Furthermore, if we ever did start to run out of oil or peak, we already know how to convert gas and coal into liquid oil equivalent hydrocarbons. Germany did that in World War II, ran their economy on a dime after being denied oil by the Allies. South Africa does it today. It also happens that the Sasol plant in South Africa is the single biggest point source of carbon dioxide on our planet, visible from outer space. But CO2 is now free, so there's no penalty to do that. The point is, we know at some price how to convert one form into the other, and could do it today even in the United States if we decided to do it for economic reasons. And in fact, the estimates are right now you could convert natural gas into liquid for $40 a barrel. We pay $100 a barrel, but nobody will invest at $40 a barrel because they don't think they can make money if they do that over the 40-year lifetime of those resources. In addition, if we started to run out of oil, coal, and gas in 1,000 years, this doesn't count the methane clathrates, the methane ices off the continental shelves, of which there is estimated to be more than all the oil, coal, and gas on our planet combined. We already know how to produce that at some level. We will get more if the question is getting that or having the lights go out. If you want to look at the oil supply curves, these come from the International Energy Agency. Here's a trillion barrel bar. That's how much energy we've consumed in human history. And We've done that for under $20 a barrel. If you want the next trillion, you can get it from known sources in the ground for under $20 a barrel. Oil in the Middle East to produce it right now costs $4 a barrel to produce, and lifting costs $6 more, and it sells for $100. Why would you open up the spigot and sell something for $50 if you could sell it for $100 a barrel if it costs you $4? If you're willing to pay $30 a barrel, you could have another trillion barrels of oil. If you're willing to pay $40 a barrel, you could have another trillion barrels of oil. The Stone Age didn't end because we ran out of stones. And the fossil energy age is not going to run out anytime soon because we're going to run out of abundant, cheap fossil energy somewhere on our planet for humans to have. I just told you there was no problem. We've got plenty of energy for a long time if we're willing to just adjust our resources and where we go get it. And if you ask the governors of Wyoming and Montana and West Virginia and Tennessee and Ohio and Pennsylvania, all of which happen to be swing states in the presidential election, they will tell you we have plenty of coal to do all that, and that's why coal is our nation's #1 energy policy. Can't be president without saying a good thing about coal. I just told you there was no problem. Now I've switched colors. Because we have to be careful what we wish for, we might get it. So we could burn all of that fossil fuel which nature has given us over the millennia in order for us to consume it all. Well, it's hard to make predictions, especially about the future. You know, we think Yogi Berra said that, but he didn't say half the things people think he said. I've traced it back to Leo Szilard and Niels Bohr, but in fact my earliest reference is Shakespeare, so I just don't give anybody credit for it anymore. But it'll never stop me. I'm going to illustrate a reasonable scenario, which is why, given I told you energy was all under control, that it's not really under control. I'm going to summarize an important paper by now a colleague of mine that I work with, Marty Hoffert, a physicist at NYU, New York University, where he summarized some important conclusions from the Intergovernmental Panel on Climate Change's 1992 report in this paper that was not about climate. It was really all about energy. So we need to understand something about how energy demand will change in the future. Here's the last century, and here's what we think the next half century will bring. And my favorite out year for this is 2050 for two reasons. One, well, I definitely see people here in the front row that definitely want to be alive in 2050, want to see what our planet's going to look like. So that's a good year to think about. Two, because unlike building a Google, where 2 years later you set up a website and you're a multi-billion-dollar-a-year company, energy's not like that. You have to build a wind farm or a coal-fired power plant. It's got to last for 40 years to return your investment. And because it's big infrastructure, that means 2050 isn't 40 years away, it's 10 years away. We are now developing the infrastructure that's going to be our powering planet mix in 2050. So we need to think about that now. In order to understand human energy demand, we need to understand how many people there are consuming energy. Well, here's the historical data for the last century. We were at 6 billion right now, and you can pick your favorite number. 9 or 10 billion people, most agree. Could be 9. I'll pick 10 as a good round number to start from. Now, to think about how much energy demand that will produce relative to the 6 billion now, we need to first factor in economic growth. Because without energy, we wouldn't have economic growth. We could decide to live in caves and not do much, and we wouldn't consume much energy. But we don't do that. We get to work, and we drive our cars, and we light our homes, and we keep warm. And in fact, per capita gross domestic product growth globally has grown at 1.6% per year on average. In this 1992, 17 years ago, business as usual, 16 years ago, business as usual scenario, the IPCC projected that we will have global growth for this scenario that is the historical average at 1.6% per year. Now, they had no idea at the time, as did anybody, about the sustained double-digit growth of China and India. The developed countries would like to see sustained economic growth of 4%. We squawk when we have near a recession of 2%. No country has a policy against economic growth, so it's unlikely this number will go negative for very long. If you take 1.5%, it's conservative, and nothing I'll tell you about will matter if it's 1 or 2 or 4%. The situation just gets worse. So I'll pick a low number, 1.5%. And you just compound these two things, and left alone, unmitigated, this would lead to a tripling of energy demand by 2050, from 14 trillion watts to 50 trillion watts. But in fact, it is mitigated because we consume less energy per unit of productivity of GDP. And in fact, we're declining globally at the rate of 1% per year historically. And the IPCC said that we expect that this baseline, that the next 50 years will bring what the last century has. For those of you that know, somewhat ironically, the United States saves energy at twice the rate of the world average. And our president has said we will continue to show the rest of the world how to save energy. We can only do that because we are so wasteful that it's easier for us to save than when you only have one candle. How much can you save? Nevertheless, this will not be easy. To maintain this 1% decline in energy intensity, we will have to do everything we know how to do starting today. Every new home will be a zero-energy home. Every new car will be a 100-mile-a-gallon car starting today. Every new building will have complete LED-based lighting in it. Because in order to just do this 1% decline and keep it up, do the magic of compound interest, it leads you to this level of average energy consumption per person within our lifetimes, 2 kilowatts a person. Here are historical data. The United States is over 10 kilowatts per person right now. Here's the European Union. Here's the most energy efficient industrialized country, Japan and Switzerland, at 2.5. At 2.5 times this 2 kilowatts. They're almost 4. China's above this line right now and growing, of course. To give you a feeling for what 2 kilowatts a person means in terms of total average energy demand, compared to the 10 we have now, humans on a 2,000 calorie a day diet are equivalent to 100-watt light bulbs. Because 2,000 food calories a day is a burn rate of 100 watts. So we have to have 100 watts just to live. That sounds low compared to 2,000 watts per person. But it takes energy to grow that food. It takes energy to move that food and harvest it, to put it into the tanker and to get it to the refrigerator from the supermarket. And all studies have shown it takes between 7 and 20 times the energy in the food to do all that other stuff. If you just held it to 10 roughly, then 100 watts means a kilowatt just to eat. And I'm going to give you 2. So we're just going to use twice as much energy as it takes to eat, on average, for everybody on our planet within our lifetimes. If we do that, we know how many people, we know GDP productivity under a reasonably conservative assumption. Energy demand, instead of tripling, would be doubled. And by the way, if we held it constant, which the world has never done, nothing I'll tell you will significantly change. Because we could easily get to 25 trillion watts from coal. We're moving that way. The world is recarbonizing in every region of the world. China installed a mind-boggling 100 gigawatts of electricity generation from coal just last year, the equivalent of 2 nuclear power plants a week they built for new generation capability. And those plants are going to be there for 40 years. So we're moving toward coal. We got plenty of fossil energy. We have no problem. We have one problem. Here's the amount of carbon emitted per unit of energy consumed. And this is, again, historical data. And we've been declining in the amount of carbon emitted to the atmosphere as CO2 per unit of energy consumed on average over our planet in a given year. We started out with wood, and that was just bad engineering. When you burn wood to heat yourself in a cave, most of the energy goes out and doesn't get to the end user. So you emit a lot of CO2 per joule delivered to the end user. Then we went to coal to power our locomotives. That wasn't bad engineering, that's just bad chemistry, because coal being essentially all carbon, when you burn it, you get all carbon dioxide. And natural gas is CH4. So when you burn it, you get 1 molecule of CO2 and 2 molecules of water. So more of the energy is produced by releasing water and less by releasing carbon dioxide. And oil is in between, being CH2 in formula, and so it's in between. These three numbers you can do nothing about because they are a property of the laws of chemistry and the heats of combustion of oil, coal, and gas. Our average, because we had equal parts of oil, coal, gas roughly on our planet consumed, was about here in 1990, but had been declining. And the IPCC said in this so-called business as usual scenario that we think the next 50 years will continue the projection of the historical decline. And so in addition to saving as much energy down to twice the level it takes to eat, we're going to project that within 50 years, the carbon intensity on average is less than that of a pure natural gas economy. The only way you can get the average value less than the least carbon intensive fossil fuel is you have a zero somewhere in the arithmetic to make the average come out less. Furthermore, to the extent that you have roughly equal parts of oil, coal, and gas, you need even more zero to get the average down to there. But we'll assume we do that too. So we'll assume very modest economic growth. We'll assume energy consumption starting today down to twice the level it takes to eat, and that we run better than a pure natural gas economy within our lifetime. Well, if we know how much energy is demanded, and we know the amount of carbon emitted per unit of energy demanded, then we can multiply the two to get simple arithmetic. And that produces this top curve. The so-called business as usual scenario, but I've outlined to you that that's by no means of anybody's imagination business as usual. The significance of that top curve is this is the amount of carbon that will be emitted to the atmosphere under that scenario. Now, there are no assumptions in this. This is arithmetic. We know that when we burn fossil energy, all of that carbon goes into the atmosphere as CO2. We also know about half of it stays there. The other half goes into the oceans and into the plant matter, the biosphere. And this corrects for what we know about how much stays. The important point is that even that scenario that I showed you is not sufficient to stabilize the atmospheric CO2 concentrations in parts per million at the numbers indicated on these graphs. If you wanted to hold CO2 to 350 parts per million, and the pre-industrial level, stable on our planet for 20,000 years, were 280, you have to follow this trajectory. That is, you can't emit a molecule of CO2 on our planet again within our lifetimes. If you want to hold it to double, to 550 parts per million, you still have to do better than that scenario that I just showed you. Now, we do not know, outside of a climate model, which levels are safe. Furthermore, we can't rely on climate models to tell us which ones are safe because we simply have never been there before as human beings on our planet. We're not very good at extrapolating these things out to where we don't have data. Right? We simply know unequivocally that even in that scenario I showed you, that the CO2 concentrations will be higher within our lifetime by a factor of 2 than what any human would have otherwise breathed. We do know from the historical record from ice core data that over the past 450,000 years, now extended to 670,000 years, that the CO2 concentrations have been in a narrow band of between 200 and 300 parts per million, but never higher. We also know that within that range, changes in the CO2 concentration have been repeatedly correlated with, but not proven to be the root causes of, I'm very careful, temperature changes that have repeatedly driven us into ice ages. We know that from human activities within our lifetimes that CO2 is now 380 parts per million, and within the next 40 years, on that scenario I showed you, even saving as much energy down to twice the level it takes to eat will be up off this chart at 550 or higher. Climate models predict average paths. The Earth isn't on an average path. It's on one path, and nobody knows which one. We do know what we see. Here's 10 years worth of summer sea ice retreat in Greenland. We know that it's melting. We don't know absolutely that it would continue to melt. We have to find out. We do know that if it continues to melt, that eventually there's enough undisputed ice there that sea level will, not projected, will rise 20 feet. We know it's melting more rapidly than the most rapid predictions of the model, so our inability to predict cuts both ways. In addition, CO2 isn't just something that affects the atmospheric radiative balance. It's an acid, as anybody that's ever drank soda pop knows. We're acidifying the oceans because of the CO2 emissions. Their pH is lower now than in several million years. Even if you fix the radiative balance, you wouldn't fix the chemical properties of CO2 dissolution in the ocean, because that's a fundamental property of that. And many, not all, although 20% of the coral is now bleached, many, but not all climate models predict that within our lifetimes, all of them will be bleached. And I tell the public that probably the only place that our kids would see colored coral is in an old movie called Finding Nemo. We don't know this will happen. We don't know that the permafrost, which was frozen, which is now melting, and helium dating of the bubbles, the helium in those bubbles that's now released tells us hasn't been released in at least 40,000 years. We do know it's melting. We do also know that the ice, which is white, reflects more light, and as it then melts, it then warms. And it releases CO2 and methane, which then is believed to warm more and then melt more. No climate model has in it these nonlinear runaway train effects because it's outside of human experience where we have data. We don't know if this would continue to melt and at what level. We do know that the amount of methane and CO2 trapped here is enough not to raise levels by a factor of 2, but to raise them by a factor of 10. We know this happened once before, 230 million years ago, in the Permian era, when there was an isotopically light, very rapid release of carbon dioxide and methane. It was thought to be one of these catalytic events, probably initiated by several things. Nevertheless, it did occur, and temperatures spiked up by 6 or 7 degrees. They remained there for a long time, and the fossil record shows that because the temperatures rose so quickly, 90% of the species then on Earth went extinct. We absolutely do not know this would happen again. We absolutely do know there is only one way to find out. How many people remember that number I told you? Oh, a couple of you. I'll tell you again. CO2 is not like ozone. Ozone is a reactive chemical that is both formed and destroyed. CO2 is the most oxidized form of carbon in the oxidizing atmosphere that we now live on our planet. That means there is no natural destruction mechanism. For the half that stays in the atmosphere after the other half goes into the near-surface ocean and the biosphere, what happens to it? It can't be removed chemically. The only thing that can happen is you have to mix from the near-surface oceans to the deep oceans. Our best knowledge says that 3/4 of that CO2 will go away in 500 years. The other will go away in 10,000 years for an average of 3,000 years, which means that within the next 50 years, we will change the atmosphere of our planet for a timescale comparable to modern human history. And nobody has a technically credible way of getting rid of the 600 trillion pounds of CO2 that will be well mixed in our atmosphere by then. If you do, you shouldn't tell me. You should tell Richard Branson, who will give you $25 million on the spot. So you're telling the wrong guy. But nobody has a good way of doing that yet. So no matter what the historical record, this is an experiment with the atmosphere of our planet that we get to do exactly once. I haven't told you the arithmetic, but to get that average energy intensity of carbon emissions down below the pure natural gas economy, even with energy conservation down to twice the level it takes to eat, you need 10 trillion watts of carbon-free energy brought online by 2050 starting today. If you wait 45 years to do it, you have 45 years of carbon emissions under your belt that unfortunately don't go away. It means starting 45 years is 44.9 years too late because they all add up. That's why 2050 isn't 2049, it is now. If you want, that just holds it on business as usual. To hold it to double, a level nobody can tell you is or is not safe, you need 15 trillion watts. The simple arithmetic to think about is if you can even hold demand to double, if you have to cut emissions by 80% of where they are now, even if you save all the energy equivalent to what we currently consume, you still have to make all the energy we currently consume out of clean energy within our lifetime starting today, or the arithmetic just won't add up. So these underscore the pitfalls of wait and see, because wait and see is wait and do. On the other hand, where in the world could we get 10, 20 trillion watts worth of power on our planet? No less developing the Manhattan Project or the Apollo space program, and these are not good analogies because all we had to do was get there. We already have cheap energy, and everybody does, so we have to fly to the moon when Southwest Airlines is already flying every hour, handing out peanuts along the way. There are only 3 sources of energy that can scale to these levels, and I'll spend the rest of the time now with a different color of slides back into the present, telling you what the laws of physics say are allowed as opposed to the laws of politics, because we get our information from energy mostly from politicians. But I'll remind you that the laws of politics can be repealed and the laws of physics cannot. Right now, the only proven technology that we have that is carbon neutral or carbon free that could scale to these levels is nuclear power. I'm personally not for or against nuclear power, but it is the only card we now have on the table. Fusion might come about, but if you take the fusion scientists at their word, they've always said it'll be around the corner in 35 years. If ITER works as designed, it would be 35 more years before it's a technical break-even. And that's not an economical break-even. And that plant, because of the radiation and neutron flux, would operate for all of 1 week before the $10 billion plant had to be destroyed. So the simple answer to fusion is one word: time. We don't have enough time. That means we have to build what we know, which is fission plants. So we hear politicians say, I'm all for nuclear power. So am I. You need at minimum 10 trillion watts. I already told you in the first scale slide the nuclear power plant is a gigawatt, about 1 billion, and that's the level at which we can build them with safety and hold that point source of heat and the neutron flux. So quick math says if you want 10 trillion watts, you have to build 10,000 new nuclear power plants. That means you have to build one every other day somewhere in the world for the next 50 straight years. That's what you're voting for if you vote not to do anything else. Oh, and by the way, the capital investment for that's about $30 trillion. World GDP is only about 45. You get to do it over 30 years, but gives you a feeling that it's not going to be cheap. There's one other little small problem. There's not enough terrestrial uranium resources to power this level of nuclear power plants for more than 10 total years. You couldn't even build the last one. So you have to complete the fuel cycle, and although there is a uranium-thorium cycle on the books, it's not proven in practice, and the only proven in practice cycle is the one that involves plutonium. So we need to think about a world where there are 10 or 20,000 plutonium-containing nuclear reactors. We should credit North Korea and Iran for stepping up to do their part to mitigate global warming. If you only build one a week, you've left 90% of the problem on the table. So where's the other 90% or more? Remember, this is just to hold it to double going to come from. Our nation's #1 energy policy is clean coal. What's clean coal? Oxymoronic without getting rid of the carbon dioxide. The thought is that we'll just put it somewhere where it won't come back to get us someday. But we emit a lot of CO2. In fact, 6 or 7 billion metric tons just of the carbon equivalent. 14 billion metric tons of CO2 every year is emitted globally right now. You could put it in the deep oceans where there's enough space, but that'll change the pH, and that's then largely technically discredited. You could put it in the oil and gas fields, but there's only about 30 to 40 years worth of total capacity there. This is where the oil companies say they're going to bury that, but don't be fooled. They're putting the CO2 down so they can make more oil come back up. The only place where there's enough capacity with a big error bar between 50 and 150 years estimated total global capacity is in the underground aquifers, in the brine under the ground, where CO2 would dissolve. And there's good news. The good news is that you'd make a lot of Perrier. You know, Perrier costs more per gallon now than gasoline, so we could export it to the French and fix our balance of trade. There's always the flip side. The flip side is it can't leak. If you're doing this for 100 years and 1% of the CO2 were to leak, then after 100 years, the flux coming back is the same as what you tried to mitigate in the first place. You delay emissions, but the atmosphere counts them all anyway when they come through. We have to know within the next 10 years what the fate and transport of CO2 will be like in a particular subsurface aquifer for the next 100, 200, 1,000 years to write the environmental impact report to let it happen. Furthermore, every underground aquifer is different, so even if it works at one site, that's no guarantee it's going to work at site number 222 out of the thousands that we will be needing in order to bury all that CO2. We should absolutely be trying to technically set up systems to project and monitor the fate and transport of CO2 under the ground, and JPL could help decide from space whether or not it actually is leaking. And are there a lot of fingers in the dikes to plug? By the way, in Texas, there are a lot. There are 1.5 million holes from exploring oil just in Texas alone. So if you think you can plug up 1.5 million holes for 1,000 years, that's a tough order. Oh, and if you plug them up, what's all that CO2 do? Well, if you take the density of supercritical CO2 at 1,000 meters and you add up all the CO2 the United States currently emits, if it's spread uniformly over our entire country, it's going to displace the surface of the Earth at a rate equivalent that after 100 years, it would lead to a rise of 5 centimeters in the ground on which we sit. This is good if sea level rises. Maybe not so good otherwise. This is our nation's #1 energy policy. We need to think carefully about getting what we wish for if we decide to do it. Oh, and by the way, what happens if the best thing you can say is that there's 80% confidence that 90% of the CO2 will stay underground for 50 years? Do you still get to bury it? And what if it does come up and kill someone? Who gets to pay? Certainly the people that buried it aren't going to want to pay, and the people that used it aren't going to want to pay, and the government that's supposed to ensure this isn't going to want to pay. So there's a lot of issues here in doing this. If you don't bury all that carbon successfully, somehow, and if you don't build a nuclear power plant a day, every day for 38 straight years, then the only other option is to not make carbon in the first place and to get your energy from a renewable carbon neutral source. And there are 5 sources. In general, tides is the 6th: solar, biomass, hydroelectric, geothermal, and wind. In the longer version of this talk, it takes about 10 more minutes, the more technical version on my website, you can see more details on each of those, but I'm going to summarize them here. Politicians love to talk about these things too. But physics dictates the allowed answers. When you look at all the potential energy and all the heights of all the water flows in every river, lake, and stream on our planet, and you add them up all combined, they're only worth 4.5 terawatts. You can't dam up the Okefenokee Swamp, and so where you can technically get it, there's only 1.5 terawatts. And although you could dam up the Hudson River, the Yankees have already fired Joe Torre, and they have to find another manager to find a new place to play. Where you can economically get hydros 0.9 terawatts, we've already installed 0.6, widely known that there's no room to grow. We hear a lot about geothermal energy. There's a lot of heat trapped in place below where we sit on every land. How much is that really? It's not the amount of heat that matters, because there's a lot of it. It's the rate at which it's delivered to the surface that dictates how fast you can pull it out sustainably. Every physics textbook that talks about the Earth tells you the number. The mean geothermal flux at the surface of the Earth is 57 milliwatts per square meter over land. If we forget to salute to the French sergeant named Carnot and assume 100% efficient heat engines, no such thing, covering the entire land on Earth, you'd only get 11 terawatts. The heat of the Earth isn't close to satisfying our thirst for energy. If you add up all the wind potential, although it's uncertain, and then decrease it by a factor of 5, why that? Because do we really want to take all the energy out of all the surface winds on our planet? No. There's 2 to 3 terawatts to be had in all the windy areas on our planet combined. It's good to use wind where it makes sense. It's the cheapest renewable energy source now, other than hydro, and it's the fastest growing. But you would have to build 2 million windmills to do that, and that is still just a tiny piece of what we would need. Here's a 20 terawatt line on a logarithmic scale. Here's all the energy and all the ocean currents and all the tides and all the waves on our planet combined is not even close. We hear a lot about biofuels. If you took the fastest growing crop and you planted it everywhere where there's rain-fed cultivatable land on our planet, and you took all the energy in the crop and counted none of the energy needed to grow it and assumed no energy needed to farm it, and you burnt it all with 100% efficiency, you might get 7 terawatts if you did it everywhere. The reason is that photosynthesis is not an optimal energy conversion machine. Plants are the wrong color. They should be black like solar cells instead of green. They also saturate at 1/10 of a sun's light intensity. And the reason they do that is they downregulate themselves because the enzyme called rubisco is really pretty rotten, and it can't accept all those electrons, and then they build up and do radical damage. And plants rebuild their machinery every 30 minutes anyway, and they spend a lot of the energy they would have made just staying alive. It's called overhead to people in academics. In fact, if you took all the land where you could grow crops and took off where we currently grow it to feed ourselves, and then added half again as much to feed twice as many people without them starving, and then took all the rest of the land and planted the fastest growing crop and assumed no energy into the farm and all the energy was burnt out, you might get 5 terawatts. We probably don't have enough water to do all this. For those of you that actually care about corn, you don't vote in Iowa, so you don't care as much. State you have to win to be president. That's why everybody likes corn to ethanol. Last year, 20% of our corn produced 2% of our transportation fuel. And we have a law going through Congress that says within 5 years we have to do 5 times more than that. Quick arithmetic says there'll be a little problem. Why do plants have a chance? And they can be material. And so if you did exhaustive planting of energy crops, you could, credible studies have shown, offset something like 30% of our transportation fuels. And that would be, in principle, valuable addition to our energy mix. But you can't get from there to here with just that alone, because plants are just too inefficient. You've got to do agriculture on the scale of agriculture, right? But they do utilize the big resource, the one big ace we have. We need 10 terawatts, and the sun gives us 120,000 terawatts. We only need 10 of them. Rick Smalley, who we lost, used to say that he believed that nuclear fusion was the ultimate answer. But we also know it's pretty good to live far away from a nuclear power plant. And 93 million miles sounds just about right. More energy from the sun hits the Earth in 1 hour than all the energy consumed from the oil, coal, gas, and nuclear power on our planet combined in an entire year. Oh, and by the way, we spend in that same hour more money buying gas at the pump than we spend funding all solar energy research in our country in an entire year. No other energy source can say both of those things in the same sentence. Photosynthesis right now powers our planet at 90 terawatts. We can't have that, unfortunately, because it's in detailed balance with respiration that makes the oxygen that we breathe. We just need another 10. If you had a 10% efficient farm of energy, not out of plants because they can't even be 0.8% efficient, the fastest growing ones on a year average. You have to do it yourself. You can't let nature do it for you. If you covered this area equivalent at a representative mid-latitude, 10 times bigger than everybody's roof is what it would take. You could generate enough energy, not electricity, total energy, to power our country forever. The bad news is it's 10 times bigger than everybody's roof. It's a lot of area. Good news is I've given this talk now for 6 years to over 100,000 people, and I've never met anybody that actually lived there. We wouldn't miss it. It's just a representative mid-latitude. You would never all put it in one place, but you get a feeling for the amount of area you would need to cover. Here's 6 3-terawatt boxes. You don't really need one in there because they don't have a lot of people, but we need to give them something else to fight over, so we'll just do that. But there are a couple challenges. One, solar cells, everybody knows, are now the most expensive way to make electricity, at utility scale, certainly. The reason is that we know how much energy the sun's going to give us over the next 30 or 40 years. It's not going to fail us. And so if you get 10% of that, then I know how much energy I can sell to you. And if it costs me $300 to put up a square meter of solar panels, and another $300 to get them installed and hook it up to the grid on my roof, then I've defined how much I have to sell it back to you at in order for me just to make up my initial capital investment over the 30 years that I'm selling you the same energy. And that number works out to be 25 or 30 cents a kilowatt hour. And fossil-based energy at generation now costs about 5 cents a kilowatt hour. So you can see that you can't get there just by improving the efficiency. You have to lower the cost, because if you're already 20% efficient and you're off by a factor of 5 just from electricity, you can't get to 100 and make it work. In fact, the cost to compete not with electricity, which don't get confused, that's high value energy. We pay dearly for electrical energy when we want and need it, because 3 joules of coal goes into making 1 joule of electricity. 3 joules of gas that could heat our house goes into making 1 joule of electricity. So we pay dearly for electricity energy, but the energy that runs most of our society, that heats our homes, that drives our cars, that runs our factories, costs even less than that nickel a kilowatt hour. And that's the China price, because if you don't get to the China price, they're not going to change. You have to be down about $10 or $20 a square meter. What's $10 a square meter? The cost of paint at Home Depot is about $1 a square meter. The cost of carpet's $10 a square meter. We need solar paint or solar carpet. We don't need solar cells that people have to hammer on their roofs, because to be fair, if you had to build 1 nuclear power plant at 1 gigawatt a day, you have to put up 1 million solar roofs every day for the next 50 straight years. 1 million. The goal in California is to get 1 million solar roofs in 10 years. We have to do 1 million in our country a day. That shows you the gap between what the politicians talk about and what physics says is the unrepealable laws of energy. The problem with solar cells is that they cost too much money. They're good for spacecraft because it's efficiency per weight that matters. It's not efficiency per dollar that matters too much to NASA. And you pay a price to make pure single crystals, but it would be great if you could use really cheap stuff like sand. It's just that when the excited electrons see the ends of these little particles, they don't hop from stepping stone to stepping stone. They lose their energy and make heat. But there's no law of physics that says that that has to happen. It's just a law of material science and chemistry that says we haven't fooled the atoms at the surface, these particles, into being able to hop the electron from site to site. We need to make a glue in this paint that lets it react and act like it was a single crystal. We need to make solar paint, which some groups like mine are working on. In fact, if you want to come to our lab sometime, you can paint on your own solar cell. It doesn't work as well yet as we would like. It doesn't last as long as we would like. But it has a chance, maybe someday, hopefully sooner rather than later, of thinking about scaling to 1 million a day as opposed to 1 million a decade. You could also think about nanowires, and I could talk to you more about that. But even if we succeed and get a solar cell on everybody's roof and on every highway, we will have done not very much. How can I say that? Because the sun has this nasty little habit. It goes out every night. Humans don't. And there's no good, cost-effective way to store massive quantities of electricity. If there were, and if you know how, don't tell me, don't tell Richard Branson, go buy it every night at a nickel a kilowatt hour from your local nuclear power plant and go sell it to all your friends and neighbors every summer day at 25 cents a kilowatt hour and laugh all the way to the bank. All right? There's no way to do that. The cheapest way is pump water uphill. That works, again, at small scale, but if you have to power every day the United States and buffer that energy every night, you have to pump up some enormous amount of water every day and every night. The way to think about it is the energy stored in 1 barrel of oil requires pumping 1 gallon of oil, it's good units, requires pumping 55,000 gallons of water up the height of Hoover Dam. Okay? Because you're trading the energy of the chemical bond for the kinetic energy of a mass of water or compressed air. None of these things that work on small scale can scale because of energy density. That's why nature figured it out. It stored sunlight in terms of chemical fuel. If we don't figure out a way to capture, convert, and store the sunlight, we will only have a peak shaving mode for some other base load that no one knows what that some other thing will be. So I didn't tell you Willie Sutton. I forgot the Willie Sutton line. So Willie Sutton was the bank robber that they couldn't catch for a long time, and when they finally caught him, they said, "Why do you rob banks, Mr. Sutton?" And he said, "Because that's where the money is." So the Willie Sutton principle of energy management would be you should go to the sun because that's pure and simple the only place really the energy is. All right? So that was the third clue. But that reminded me of my other line here, which is we have a big problem with storage, and Johnny Cochran would have said, "He that cannot store shall not have power after 4." Right? What you would not do is if you had enough biofuels is you would never take a superior fuel which had carbon-carbon bonds and, like the Department of Energy's website said, put it into a machine and pay dearly a penalty to make it into an inferior fuel, hydrogen that's a gas. You would never do that. You would refine this, run that as biodiesel in your cars, be carbon neutral, and declare victory and go home. If you ever had electricity from the sun in large enough scale, you would never convert that electricity into low-value energy. Instead, you would just use it as electricity when you could. The missing link is how do you make sunlight directly into stored low-energy chemical fuel, which is the thing that powers 90% of the economies of our planet. That's what we don't know how to do. Here's the hydrogen economy today. You would take this parabolic double-axis trough and you'd focus it on this external Stirling engine, or it could be a high-efficiency concentrator cell. And you would use that electricity made at 30 or 40% efficiency to put into this electrolysis unit to make hydrogen. Probably has half the world's supply of platinum here. And every day, this plus this would fill up that tank with hydrogen. Doesn't look too good. And you would have to build one of these every second for the next 50 straight years. That's the scale problem. There's enough platinum in here, by the way, although we build demonstration fuel cell vehicles. You should understand that the only good catalyst that we have is platinum, And we demonstrate systems with platinum, the same one we've had for 50 years, which was first flown on space flights, still is used on space flights. Again, it's per pound, not per dollar, that matters there. But when the amount of platinum in a fuel cell to power a school bus costs $500,000, then the hydrogen economy will be very vigorous, consisting of stolen school buses, right? The driver is going to say, "See ya." He's going to head right to the refractory meltdown place with that engine. We need to find a way to make that fuel without those expensive catalysts. We need to find a way to make it directly from sunlight because wires cost too much money and electricity is high-value energy, and we want to directly make low-value energy. It's foolish to make high-value energy and then pay a dear penalty to make it again into low-value energy. Nature knows how to do this. Nature, in bugs, like this little bug, has an enzyme that doesn't have platinum in it. It has iron in it, a really cheap metal. Fuel cells with platinum are poisoned by carbon monoxide and sulfur. It uses them in the molecule. Nature said, "I don't want to worry about that. I'm going to put it in and make it useful for me." We are just now pulling out, as chemists, these enzymes and building model structures to try to get them to function just like that. And this works at the thermodynamic potential, so it doesn't waste any first law energy in catalyzing electrons into hydrogen, for instance. Nature can also fix CO2 and fix carbon-carbon bonds. Nature also knows a way to make oxygen from water. That's what this manganese site in photosynthesis does. That's why oxygen is in our atmosphere. We now finally have the crystal structures of where all the manganese atoms are, and chemists are building models to try to catalyze this. But we don't have them yet. So in summary, we're going to need more energy because we all want economic growth, and we have population growth, and even if we hold energy down to double or keep it the same as it's ever been, you still need daunting amounts of carbon-free energy in order, if the goal that you want to satisfy is to cut emissions so that carbon dioxide levels don't continue to build up. Remember, we talk about slowing the rate of change. Well, of course that's necessary, but slowing the rate of increasing your credit card charges every month doesn't help you get out of debt. It just doesn't make it much worse. The debt, in this case, is going to last for modern human history. All right? The first thing of any serious energy discussion must be energy efficiency, which I built in down to twice the level it takes to eat. If you don't save energy, then you have to make even more energy in order to make the arithmetic work out. It's cheaper to save a joule of energy than it is to make it. And every joule that you save avoids making 3 joules at the source because of inefficiencies in the whole generation system. So it's clear that if you don't save energy, that this problem becomes from pretty hard to almost impossible. So we absolutely have to do that. On the other hand, no amount of saving energy ever put food on somebody's table. No amount of saving energy ever turned on a light bulb. You still have to make enormous amounts of clean energy within our lifetime starting today. If you wait 45 years, you have 45 more years of emissions under your belt that don't go away. On the supply side, there are only 3 big cards. There's coal, if we can sequester it all, if we dare. There's nuclear power plants with plutonium, if we double dare. And there's finding a cheap way to utilize the biggest resource that we have, which is the sun, to make something that we can store massively so we can deliver it to people whenever and wherever they need it, and without which you don't have much. Needs to be cheap because we already have energy, and nobody's going to pay 5 times more for something they already have. This is not like an iPhone. It's not like a cell phone when there was no other way to drive your car. You already have energy, and you're not going to pay 5 times more just to have the same thing you already have. So it's got to be cheap. I haven't talked about policy at all. I've only given you technical facts. But I'm going to wrap up with asking the questions, not answering them, because I well know that it is not a scientist's job to make policy. It's a scientist's job to tell you the scientific facts and leave it at that. There are two opposing positions. One that says this will cost money. It'll ruin our economy. We can't afford it. Of course this will cost money. You can't take a developed, mature, massive, $2 trillion a year in the United States energy industry and expect to wholesale switch it within one generation and not have it cost money. It's clear it will cost money. You can't, however, do a cost-benefit analysis because we have no idea what it will cost us if we don't do it. That's not a fair question to answer because scientists can't help you there. The flip side is, instead of saying it's something we can't afford to do, is saying it's something at which we simply can't afford to fail. Because we get to do this uniquely as members of our planet exactly once. No other generation is going to be in this position because fossil fuel consumption was very low 50 years ago, and it is the base level now that is the source of this problem, and it's not going to go away unless we stop burning it within the next 20 years. So we need to think about whether or not we are treating this as something that's just nice if it works, or something at which we can't afford to fail. If the answer is the second, then I assert things have to really change. You know, when the DOE's basic science budget is less than the NIH's budget increase, we're never going to get there. When we pay more money in 1 hour to buy gas at the pump than we spend funding on all the solar energy research in our country in an entire year, we are never going to get there. You can't redo a $3 trillion a year industry on 0.01% of revenue spent on R&D. When you look at the percentage of revenue spent on R&D, the electric utilities spend less on R&D as a percentage of revenue than the dog food companies do. If you believe in putting your money when your mouth is, then we're going to the dogs. I think we could do this. But to do it, we would have to be serious. We would have to really mobilize both the political will and science and technology to help develop a low-cost, scalable solution to this problem in a mode that we as the country says, it's not okay if it works, it's just not acceptable that it fail. And that's the mentality we have to be in, not in 50 years, but unfortunately, because CO2 doesn't go away, that decision is ours. So with that, thanks for listening. I'm happy to answer questions. There are always questions. Yes?
Which presidential candidate understands this and will lead us to it?
Oh, I am apolitical about this. So all I can tell you is that the stated public presidential candidate positions on this are that the two Democratic candidates have stated that they would try to assess cap and trade legislation that would cut emissions by 80% of current levels by 2050. It would get us close to this curve. But there are always escape valves in these legislations, that if it costs too much money, then we'll remove the caps. Well, it's going to cost us way too much money unless we do the R&D to lower the cost of doing this. And so those caps are useful only because it'll be the next president who will have to figure out how to deal with it. Right? On the Republican side, all but one of the presidential Republican candidates have been silent or opposed any caps on carbon. The one exception to that, who had a bill in Congress with Senator Lieberman, happens to be John McCain. And he has pushed through, unsuccessfully authored a bill that would cut carbon emissions by 65%. They make up the numbers. Sounds good. 60 sounds better than 20. I mean, there's no scientific basis to have the real numbers. It's a step in principle in the right direction. But understanding the implications of what those numbers mean to our energy system and what it would take to actually do it is a mismatch between the technology life cycle of 40 years of capital investment and of energy demand, and the political cycle, which is get elected in the next 4 and then worry about it when someone else fixes it. I will say one thing, not political, just I think economical. I'll venture out of my expertise. We certainly have a policy now of voluntary cuts. All right? So how well has that worked? With all the talk about Kyoto, emissions of carbon dioxide were growing from the 1990 to 1999 by 1.1% per year. And then we really talked about it, and we buckled up our belts, and we showed the world what we could do. And between 2000 and 2006, we tripled it. And now we're at 3.1% per year. So that shows you what voluntary emissions are doing. Look, when something is free, you know what economics tell you. You take 10 of them. Right? 10 newspapers for free, not just one. If you don't set a price on something, then there's no way to motivate people. Why would you build a carbon sequestration plant that has no reason to exist other than to take something which is free and put it under the ground if you can't make money off of doing that? Right? So that industry can't happen, if it happens at all, without a price on carbon, directly or indirectly. We're not willing to do that yet. I mean, our nation's real #1 energy policy is 2 words, cheap gas, right? We still talk about it today. Nothing can happen to change the price of gas that would make it go up. Of course, the best thing for climate would be to make the price of gas go up, right? Because after all, it's so cheap that even when it goes to $3 a gallon, people still drive as much as they ever did, or more. It was pretty apolitical. Let's go back there, yeah.
I was just wondering if you could tell us a little bit more about the effect that global temperature increase might have on the large methane clathrate deposits.
Yeah, she asked if I could tell you more about it. I'm one of the number of scientists that is reasonably knowledgeable about the climate models. And so that is a lens through which I view what I'm comfortable as a scientist telling you what we can robustly say. Unlike the people that run the models, who are paid to run models, and that's their stake, the observers of the models see many, many flaws. We can't really predict, you can't predict the local regions of much of anything. And if you get the weather wrong for 3 months over Oklahoma, but get it right over Texas, is that any better than missing it in Texas and getting it right in China? Is it better to get the humidity right in the northern hemisphere or the average temperatures right in the southern hemisphere? All climate models on all runs miss a whole lot of things at levels of error that are much higher than the 1% perturbation in the radiative forcing that a doubling of CO2 would actually incur. So to then take, and furthermore, we don't really know the initial conditions because we don't know the amount of cloud cover that was there at 1900 or 1950 simultaneously everywhere on the Earth. We don't know the temperatures everywhere. We don't know where to start. And so you start with sparse data and you run the model, and then you run it again with different data, and you run it again and again, and you take the average path. So the average paths are the things you hear about, but it's clear the Earth is not on an average path. We're on one path, and no one knows which one. That's where I'm comfortable stopping as a scientist. I can't tell you at what level the CO2 permafrost might run away. It might be 380 where we are now. It might be 550. It might not be till 780. So if a scientist tells you that they will be able to say what is safe, I don't think they can do that. They can tell you what we see, and they can reasonably say that more sounds like it's worse, but we don't know that for sure either, because there are negative feedbacks as well as positive ones. And we simply haven't been there as a planet before, so it's very dicey to say what will happen. This is why, I completely accept the fact that some skeptics, quote, say that it won't be very bad at all. It might be better. Oh, they're right. There's some probability that even though for 700,000 years, every time CO2 has gone up and down, so have temperatures, that this time that won't happen. It's just that we only get to do that experiment once, right? So that's the real knowledge that we do have. Yeah?
What type of solar thin film cells you think are more likely to succeed?
There's flux in this industry right now, in the solar thin film cell industry. There are 3 or 4 candidates. Cadmium telluride is one, copper indium diselenide is another. All of these, of course, 90% of the market is still multicrystalline silicon cells that have been lowered in cost, but are the same technology, basically, with some improvements as what JPL worked on for spacecraft in the 1970s, when JPL was a center of excellence in the nation on flat plate solar arrays, actually, at the time. They cost less now and are made in larger scale. There are several states and regions and countries, Germany and Japan, that have buy-in tariffs, other incentives. California has an electricity renewable portfolio standard. And so there's a growing market for solar because it's the really only large-scale way to meet those, even though it costs much more than current electricity generation prices. And we're now in a situation where you can sell anything you can make. So we're capacity limited as an industry. So even if you make something like cells that aren't really energy efficient, that really cost more than the next guy's, someone still has to buy them to meet their portfolio standards. And so these other thin film technologies may well rise and then may well fall market share again. The silicon people say the price of silicon is going to come down and we'll cream all you. And the thin film people say, no, we're going to roll them out like carpet. It's in a lot of flux. We don't know what the answer is. It would be a good step forward, but as I told you, A, a large area, 10 times more than everybody's roof, and B, 1 million a day, and C, if you don't store it, you still don't have much.
What do you feel a sustainable number of human beings for the planet would be?
Okay, that always comes up because mathematically, of course, there's a mathematical solution that says the other way to cut emissions by 80% is to keep using energy at the rate we do and cut people by 80%. It's mathematically allowed. You believe in democracy? Everybody gets to vote, all right? Well, you use as much energy as 4 Chinese and 10 Africans. So now if we all get to vote, who do you think's going to be the first billion people or so that are going to have to go, right? And by the way, if it was those Africans, they don't cause the problem, so it wouldn't fix it anyway. So this is a case where mathematically allowed isn't practically allowable. Yeah.
I have 2 questions. The first one is, what can the average person
Good.
do to help?
Great. So I should talk about that, and that comes up a lot. There are 2 different modes that the average person can do. One, I did say at the end, energy efficiency is a no-brainer to do. You can save energy and save money, right? It's a no-brainer to do it. I changed my light bulbs 2 months ago. It cost me $200. I saved $220 the first month in electricity. I'm going to save that for 7 years. Where else can you get a guaranteed 100% return on your investment every month for 7 years? So we should just all do that, right? We should all beat on everyone to have more energy efficient cars and so on. That's what individuals can do. Unfortunately, we don't as individuals have control over where our energy comes from, right? That's where we trust our public utilities commissions, our departments of water and power, like in LA, the MWD, our senators and congressmen, and we have to beat on them and let them know that if there is an issue that matters, if we're going to be single issue voters, this is the one we're going to vote them out if they don't deal with. That's what you can do. Yeah.
Can you speak on using central collector solar plants instead of voltaic cells? And how are they more efficient in comparison?
Okay, so I showed you a Stirling engine, but that could have been a multi-junction. He's asking of what about central collectors? So there are two strategies for solar electricity for photovoltaics. One is flat plates like you see on people's rooftops. The other is, like I showed you the picture, is concentrating the sunlight, and you can use it more efficiently because it's focused, and you can afford a more expensive solar cell because you're using a lot less of it and making cheaper lenses. But you have to track the sun. Right? Furthermore, they don't scale down so well to rooftop levels. They're better at large-scale installations. And they compete in two different markets. Solar cells that you buy with tax rebates can amortize out to be about 25 cents a kilowatt hour. And you can avoid some peak electricity costs that may be a little more than that even, and save money over the long term. But they compete with retail, and they don't pay for storage and pay for the grid. You just got to hook them up, right? And then solar concentrators are at utility scale, and they compete at cost with utility generation costs from coal or nuclear, which are about 5 cents a kilowatt hour. They cost 10 to 15 cents a kilowatt hour. They're cost disadvantaged in their market. Solar photovoltaics cost 2.5 times more, but are cost disadvantaged maybe by a little bit in their market. So they serve different markets, and they have their equal own problems, even though the efficiencies are very different. The biggest problem with concentration